Guys, to run a principal component analysis, I'm going to call it my PCA. I can use the command PRINCOMP, and I can run this on my data. I want to run a scores equal true command, and I don't want the covariance, I want to use the correlation matrix, so correlation equal true. Now, if I run my PCA here, and that's not what I want to do, actually I want to run my summary of PCA. Keeping in mind, forget this right here, guys. You're never gonna run this, so eliminate that from your notes. So you're going to run a summary PCA, and again, let's think this through. I have 4 variables, right? Attractiveness, or whatever they were: appearance, knowledge, education, and personality. So what I'm going to end up with here is I'm going to end up with 4 components. And if you look at the components, we have an importance of components table here. And we can see that the standard deviation for the first component is 1.419966. Now, that should look really, really, really familiar if you're really, really, really good at squaring numbers, because that turns out to be exactly what we get on our diagonal of the L matrix. So this L matrix gives us the variance of component 1, which is the eigenvalue, which is just the standard deviation of the component squared. Guys, if we take 1.3933821 and square it, you should know that you're going to get 1.94, which is the value on the second diagonal. Now, all these, it'd be nice if these were showing up zeros and within, certain numeric restrictions on numerical techniques here. That's what we're actually getting on the other components, but or I'm sorry, on the other elements of the L matrix. Now, what's actually happening here is if we look at the proportion of variance, component number 1 is explaining 50.4% of the variance that the 4 observed variables explains. Component number 2 explains 48.5% of the variance. And component number 3, which is, notice we're dropping off each case, with each component, only serves to explain about 1%. Another really important row is this last row, which is the cumulative proportion. So the first component, 50-some percent, adding in the percentage of variability that component number 2 is explaining, we can collapse our total principal component analysis from 4 components, from the 4 variables, down to 2 components, and these 2 components again explain almost all of the variance in the 4 observed variables that the 4 components do. So I'm sorry, the 2 components explain 98.9% of the variance that all 4 of the observed variables explain. Now, once we run our PCA, there's some things that we want to run and take a look at. First thing I'd want to look at is just a plot. And if I run a plot of my PCA, I get something kind of cool. What this does is this gives us our variances, and just as we saw here, the variance in the first component is 2.01, so it's slightly above 2, and so on and so forth. To me, and it doesn't work out like this always, but to me, this is clear that we have what's called a 2-component model, because component 3 and component 4 aren't adding much variation or explanation of the variation in our overall model. So just a picture, and there's a way that you can actually draw. If you take a point right here and a point right here, you can connect that line, and there's a way that you can determine where your cutoff should be in terms of your components. But this one's not a very good, well, it's just an inappropriate example, but I wanted to keep it small for obvious reasons. Next thing we may want to do, and this is the one I think really makes things kind of come to a heart, is called a biplot. Now, this is going to give us actually vectors of our components. So component number one, and again, we're living in 4 space here because we have 4 variables. So component A and P, notice that, what was A and P? That would be appearance and persistence. Notice they're pointing in the same direction and approximately the same magnitude, whereas K and E are pointing in opposite directions, but notice that their magnitude is very similar. So that's telling me that my natural loading is that factor 1 or factor 2, whichever it may be, will load on one factor. So A and P, which was appearance and personality, load on one factor, and the other factor would be knowledge and education. That's kind of cool the way that actually turned out. Okay, something else we may want to do is look at what we call our PCA loadings. And our PCA loadings actually give us the correlations between the variable and the component. So we can see that the first variable, which is, I keep forgetting, education, only has a 0.35 correlation with component 1, whereas personality and appearance are highly correlated with component 1. Now when we get into factor analysis, what we're looking at there is we're going to see that personality and appearance are actually creating factor 1, because what we'll do, we'll take 2 components here and we'll ultimately create 2 factors from the number of components. And component number 2, you can see that the other 2 variables were most highly correlated. Now we're not really interested in the negative positive, but we're interested in the absolute value of that. Component 3 primarily drops down because there's very little correlation between component 3 correlation. Okay, that kind of surprises me. We only got a 0.2 correlation here, so all right. This is what happens when you get an extremely small data set. You get kind of wacky things here. Now, let's let me see. What do we want to do here? Let's go back over to the paper. All right, gang. Now let's just so we're clear on. So we've got R is our correlation matrix, and we saw that V has the columns, and we'll just call that the eigen vector matrix. Okay. Now we saw earlier that L was V transpose R V. And it shouldn't take many operations to convince yourself that we can solve for the correlation matrix here by taking V times L times the transpose of V. I'm going to leave this connection to you. It's just remember matrices are not commutative, and but you should be able to make that happen pretty easily. So guys, at the end of the day, what we can say here is that the correlation matrix, which is this R, can be expressed as the product of, darn it, the product of the eigenvectors and the corresponding eigenvalues. Now, I want to look at this a different way too. I could take R and re-express this as V times the square root of L times the square root of L. And remember, this L was the eigenvectors. I'm sorry, the eigenvalues. So we can take the square root of those values, which would be just essentially taking the square root of the diagonals. And we can reposition this or reassociate this way. And we can think of this as two new matrices that we can just call A and A transpose. So we can rethink our correlation matrix as the product of A times A transpose. Now, I'd like to demonstrate this for you, and let me see. What I want to do here. All right, gang. This first matrix that we look at here, this A matrix. Let me start a new sheet of paper. Is actually in factor analysis and principal component analysis, this is what we call an unrotated factor loading matrix. And remember, this thing takes a little bit of work, especially in R. The V is not going to be a problem, but the L is. Okay. So what I want to get back over in R to do is, and here's what I want to do. Since we have already run the principal component analysis with 4 components, and what we found here is that C1 and C2 explain, I think, right at 99% of the variation that variable 1, variable 2, variable 3, and variable 4 we'll say that we have a 2-component model. So what I want my V to be is it's going to be a matrix for component 1, component 2, and of course variable 1, variable 2, down to variable 5. And then I want this matrix to be the square root and zeros and zeros here. So the product that I'll get from this will be the unrotated factor loading matrix that we'll use to actually start the rotation process that we looked at earlier graphically. So we need to create this, and you know, I'm probably pretty sure that the way I'm going to do this is not optimal. I have to be honest with you, I really don't know how I'm going to do this just yet. But what I want to do is I want to come back into my V matrix that I have right here, and the only thing I want are just the first two. The first two. Is that right? Yeah, I just want the first two columns. So I'm going to create this matrix called V1. And as I forgot how to do that, to just pull that out. So what I can do here is I can go, so what did I call the eigenvectors? Just V, right? Okay, so I can go V $ vectors, and then I can go 1, 2. So I'm going to choose just the first two columns. Let me make sure. Okay, why is that not working? Oh, okay. V1 was V was the vectors. Okay, so I don't need all that. So I just need V1. Okay, this will work. So guys, what you can see is I just came in and pulled out that, right? Yeah. All right, cool. Now, what I'd like to do next is I'd like to bring in, create a new matrix of the square root of the eigenvectors. Or, I'm sorry, the eigenvalues. And that would be the square root of and I'll tell you what I'm going to do. I'm just going to go ahead and create the diagonal of L, and I'll have those numbers there. So what I'd like to do now is I'd like to create L1, which is a matrix of this. And I'd like to have the square root of 2.01 63054 05104. Next I want 0. And next I want 0. And then I want the square root of 1.941513 814. All right. Then I want n numbers of rows to be 2, and columns to be 2, and by row equal true. Okay, exactly. So gang, now if I'll take, I can create my A matrix by taking my V1 times my L1, and this of course gives me my initial factor loading before I get into any sort of rotation. Well, boys and girls, I think that I am over time, or at least close to time. What I'm going to do next video, I'm going to upload probably more of this. And you know what? I may go through. I take that back. I think what I want to do is illustrate a fuller example, and yeah, I think that's what I'll do. Anyway, I'll make the decision before then, and let you guys know. All right, take care.